Hello, everyone. Thank you for attending this talk. Today, I'll be discussing about how we maintain and build a managed Jupyter environment, Jupyter notebooks experience at Uber. Along with that, I'll also explain some novel ideas that we came up to maintain snapshots. Let's go ahead with it. So I'm Chan. I've been working at Uber as a senior software engineer for past 2.5 years. I'm primarily a backend engineer in the data platform space for around 5 years. So within this data platform team at Uber, I currently lead the data science workbench charter, which is a managed platform for both Uber and RStudio. Today, I'll be focusing on mostly Jupyter. So before going into the talk, how many of you have used Jupyter notebooks? Oh, that's a great deal. I'll have easier time to explain what Jupyter notebook is and how a managed instance of the Jupyter notebook would look like. So let me just show you the offering within the internal offering at Uber. So this is how it looks like. So you can go ahead and create a new session. You can provide the name of a session. You can create a type, use a type, how large the session you need. Which data center you want to spawn this session in. And there's something interesting called available snapshots, where these snapshots are, some of the snapshots are provided, some of the snapshot you can also create when you create a session, you install some custom packages and you want to reuse the same snapshot in some other sessions. Along with that, we have some bookkeeping ownership information that is not relevant for this talk. I'll show you how it looks like once you create a what happened. Sorry for the interruption, just a minute. It's just it probably is loose. Yeah, directly connecting to it makes more sense. All right. So this is what it looks like when you open the Jupyter Classic interface in a session that has spawned up. You get an interactive access to Python. Along with vanilla Python, different vanilla Python environments, we also provide some PySpark and Spark Magic related environments where you can directly interact with the Uber's data lake through these kernels. This is how it looks like in terms of experience. I'll go in detail and how we manage these snapshots and environments. So this will be the agenda mostly. So I'll be I have already shown you the notebook experience at Uber and what was the philosophy that we used to build this tool, the architecture, high-level architecture, how we managed, how the managed Python environments are maintained, the challenges we face it, challenge, then just listing out the challenges. I'll try to show towards the end how we can maintain a layered environment using a POSIX compliant distributed storage so that we can reduce redundancy. So this was just a demo which I already shown. I'll just skip over it. So this is the philosophy that we used while building this managed Jupyter experience. We wanted to have a quick access to exploratory coding. So anyone accessing this will be able to access Uber's data lake, all internal tooling, no need to set up any environment. So the boilerplate you can you can just access an Python environment without any hiccups. So this is how the high-level architecture looks like. So we have Uber Compute built on top of Kubernetes. It's also a managed service within Uber where compute is provided to our team. The user can come and create a flavor of a session. It could be Jupyter, RStudio, and within this Jupyter session, multiple Python environments will be available, including PySpark and PySpark plus Spark Magic, which can be accessed through browser, either through Jupyter Lab interface or Jupyter Classic, or through VS Code from your local laptop. In this talk, we'll focus on this aspect of the architecture, how the environments are managed, and how the user can extend it, create new snapshot, and reuse it. I have already shown how we maintain 3 versions of Python. It's basically mini-conda environments where you can install new packages as you want. We also provide some base packages as part of the snapshot. And we also provide 2 different flavors of Spark. One is vanilla PySpark, where your Spark driver runs within the session itself, and your Spark executors are spawned remotely. And then we have PySpark plus Spark Magic, which interfaces with internal deployment of Livy, where your entire Spark cluster runs remotely. We also allow automatic distribution of the Python packages through HDFS. I'll give an example how we do it. So the primary challenges that we face while building this is how you make it reproducible, so that once a user creates a new session, installs new packages, it may happen in a distributed container orchestration that the session goes down. So the entire process of creating that session has to be repeated by the user, which reduces developer productivity. So in order to solve this, we will have to solve for reproducibility. One aspect of is using the same snapshot in a different session, and another aspect of is allowing your current environment to be distributed on the Spark cluster. The second challenge that we had was extensibility. So we had, per session basis, we had to give the user a way to install additional packages, be it custom, be it some packages installed from PyPy or internal Artifactory. In order to do this, earlier what used to happen is for every session we used to download these snapshots, which can be in range of 5 to 10 GBs in every session, and that takes some time. So when you create a session, it takes about 5 to 7 minutes to spawn because of downloading this, unpacking this, and setting this up. And we understood that this is a redundant steps, as all these base snapshots are kind of common and being used across sessions. Why can't it be a single layer? So the reproducibility aspect of it, we solved it through snapshotting, as mentioned. I'll go through the architecture of snapshot in the next slide. The distribution of Python packages, it is fairly simple how we did it. We forked the Spark Magic library available in the open source. So when you create a kernel, Spark Magic kernel, what we do in the fork library is we archive whatever packages you have in your environment. We upload it on HDFS. And then we just, in the Livy configuration, when you're creating the Spark Magic, we just update the HDFS path on the archive field. So when the Spark session bootstraps, it downloads those package from HDFS and unpacks it. And it becomes available throughout your entire Spark cluster. So this is the architecture which we use to snapshot Jupyter environments. So we have a stateless, horizontally scalable snapshot service. So every time the user requests for a snapshot for a particular session, we acquire a Jupyter log. We take the list of the packages that are present in the session, and then send that package to the snapshot service. It downloads all the packages from the Artifactory, archives it, and keeps it in an object store, which again will, now once the snapshotting is done, this snapshot will be available to be used in a new session that I have shown earlier. So for extensibility, there are 2 ways to install new packages in these Jupyter kernels. One is to use just the %pip cell magic that is available with the recent version of Jupyter. And then we have also introduced some install scripts which intelligently manages and installs the package in corresponding kernel environment without the user having to intervene anything. So the reason why it is important is in a particular Jupyter session, there are 5 or 6 environments there. So the users need to install the package to the corresponding environment for it to be available. Otherwise, if I install a package in Python 3.6, it won't be available in the Python 3.10 kernel. Uh, Earlier, I explained uh, what this snapshot does. So it kind of creates a redundant duplication where you download the same snapshot again and again whenever someone is creating a new session, right? So we came, so while we realized this problem quite before, didn't have the time to execute it. We understood that if we can have some sort of a layering environment where the base snapshot is present on the POSIX compliant distributed storage, by the way, which that POSIX compliant distributed storage is attached with every Jupyter session. So if the base snapshot is available in the POSIX compliant distributed storage, we can create Conda environments per session, which is fairly quick task, which takes about 30 seconds to create. And then if you install a new package, it goes to your session specific environment. Otherwise, if you are importing a package which is already present in the base environment, it loads that package from the distributed store. So that every time when a new session is created, you don't have to download the entire snapshot, but you can just reuse the same. But there are a few challenges. How do we achieve it? We were searching for tools, how we can tweak the Python path, Python search path of the modules, and then achieve these things. While going through the Python documentation, we found a very nifty way to do it, which is also pretty stable. So this is how it looks like. So as I said, every session has a distributed storage attached to it, which is, by the way, POSIX compliant. And then the base environments that I have shown earlier are write restricted and with basic set of packages present. Now, a session comes up, it has its own kernel environment, Conda environment. The user can install a package there. However, if the user is referring or loading a package from the base environment, it gets loaded from the distributed store rather than loading it from the session's own environment. So this saves us redundant downloads every time. So this improves the bootstrapping of the session. This brings down the session creation time from 7 minutes to 2 to 3 minutes. So I'll quickly show a demo of it, how we can achieve layered environments. I already have it pre-recorded. So this is my home directory within a session. And this is the path where all the Python environments are present. So we activate an environment and see if a certain package is present in the environment or not. So PyPostmaster is our Uber's internal Python SMTP client. So we see that in the Python 3 environment, PyPostmaster is not present. We deactivate the environment and go back to, and also check in another environment, Python 3.7, whether it is present or not. So it is in 3.7, it is also not present. So we deactivate and go back to home. What we do here, we simulate the distributed storage aspect. So we create a new directory here, base packages. We install PyPostmaster in this base packages directory, which simulates the distributed store. This is one aspect of bookkeeping that we have to do. We have disabled pip usage from the terminal for obvious reasons. It may corrupt the entire environment. So now I install PyPostmaster in the base packages directory in my home directory, so it goes ahead and installs it. So if you see, PyPostmaster 1.9 is installed. Yeah, now we go back to the environments I have shown earlier. And what we do is we create pointer files. These are supported by vanilla Python. We create pointer files. These pointer files points to a different directory for the Python search path. In this case, in the Python 3.6 environment, we create a pointer file to the base packages directory that we created just now. So once this pointer file is created, now if we just check if PyPostmaster, we will just activate the environment and see if PyPostmaster is present. We didn't install the PyPostmaster package explicitly in this environment, by the way. So we'll just see how it works. As you see, the PyPostmaster package is installed and it is being loaded from the directory that we created. So this is being loaded from the layer 0 of the environment, while the same package can be used in a different environment as well. So we deactivate this environment and activate the other environment in Python 3.7 just to show you that in Python 3.7 this PyPostmaster package is not available. As you can see, it is not available. We create the pointer file in this environment too, and the PyPostmaster package will be available there. So let me just quickly skip this. Yeah, just ignore this. This is some didn't related error messages being printed on the console. So again, we create the pointer file in Python 3.7 environment. And we try to see if PyPostmaster is present, and it will, if it gets loaded from the base environment itself. Yeah, so as you can see, this in a different environment, the PyPostmaster package was loaded from the same base directory that we created. Now, one aspect of this problem is, what if someone deletes the base environment altogether, right? And then all the packages will be lost for every session to access. So that's a problem. For that, what we can do is we can change the permission of the base environments. We can make it write protected, as well as we can change the Unix attributes of the directory to make it as immutable, so that it is accessible for reading purposes, but not accessible for writes. Even the admins, if the admins want to delete the environment in the base layer, because it is immutable, it will throw a caution so that we have an added guard to not delete it. So I'll just show what happens if we just change the permission of the base layer. So we'll try to uninstall it. Because the package is not present in layer 1, it will throw an error. So I'm just checking what's the current permission bits. It's read write. So I just update the permissions of the base package. Yeah, so the permissions are updated to be write protected. Now, if I activate the environment and see what happens if I try to delete the base environment files. So I try to install the PyPostmaster package, which is present in the base environment, and if I do this, it says permission denied. The file cannot be deleted. But if I just activate the Python interpreter and try to import it, it is still available from the same location. It is importable and usable. So that's it mostly for the demo. I will discuss a few more things. So in order for making this, in order to make this snapshotting a very efficient tool for developer productivity, we need to target distribution of these packages on Spark cluster. What happens today is if you are iterating on a Python package, you have distributed to Spark cluster, and while bootstrapping, it has loaded up the package, right? Now, let's say you have updated the version of the package, or you have installed a new package in the Spark cluster, in your kernel, but it has not distributed to your entire Spark cluster on the driver and the executors, right? For it to happen, you need to restart the entire Spark cluster. So that becomes a problem because restarting a Spark cluster can take 4 to 5 minutes and even more than that, depending on how many nodes you have. So in order to solve it, what we are trying to do is we are trying to mount a distributed storage in every Spark node. While we install a package, we install it in the distributed store, and if after installing, we just restart only the Python runtime within the Spark cluster. We don't have to restart the entire cluster. That almost works instantaneously. It is in the works. I could not show the demo. This is what is coming into our platform. So that almost, so whenever you are iterating and installing packages on the go, it almost restarts the cluster instantaneously without the user knowing what happened behind the scenes, and it installs the packages. One more thing that we are trying to do is serverless access to Uber Data Lake. It is, we took the, we took the idea, we understood the idea what Facebook does. They have a similar system called Bento, where they provide Pyodide-based Python kernels. We are trying to extend that and provide our read client for Uber Data Lake within the serverless aspect, so that when you create a session, you don't have to actually create a physical session on Kubernetes. Your Python code runs on the browser, and you are able to access Uber Data Lake for any analytical reasons. So that's mostly about it. Any questions? Okay, if you have any questions, if you could come there.
Yeah, it was a nice talk.
Thank you.
And I just wanted to ask, if I have 2 pointers in an environment, what will be the logic of resolution?
So the logic of resolution would be, if I remember it correctly, it would be alphabetical order, or in the pointer file, if you have 2 locations, it will go by that order, right? So if you have location A and location 2, if you have a package present in location 1, it will pick up that.
Thank you.
But if you have multiple pointer files, then it becomes alphabetical. That pointer files are picked up in an alphabetical manner. Any other questions?
Not strictly a question, but
okay.
Good to know the benchmark of 7 minutes reduced to 2-3 minutes. Are you further exploring it to make it even more shorter?
Yes, the bottleneck for that is since we have the session images present on Artifactory, right? And for every time we release a new session image, that has to be present on the Kubernetes hosts. And each session image, again, is 10 GB, which takes time. So it's kind of variable. We are exploring some ballooning options where if you release a new image, we make that image available on all Kubernetes hosts. So the bulk of the rest 2 minutes is taken by Kubernetes to actually download the image and store it and start the session.
So recommendation, so there's a Rust tooling coming in that to solve the problems in that area. I'm sure you heard about a product called UV.
Not really.
So Yeah, I'm working with the team. Now we have a BOF in next 5 minutes. If anyone is interested to listen to that,
We can
please
catch
join.
up, certainly. Yeah. Any other questions? All right. Thank you then.
Thank you, Sayan.